Welcome back. I got a drawing tablet, so now I'm gonna start making a bunch of Khan Academy style videos, but I'm not good at teaching, nor am I good at anything else other than a bit of physics and math. So that's what I'm gonna do. Today I'm gonna do, what do you call a free fall problem. There you go, physics. We should use a solid arrow. So this is going to be the y, that's the x, that's the ball that's being thrown and is falling. Pretty exciting stuff. But we're going to do this using actual math, real math, not just algebra. We're not just given the, the equation of motion for free falling or constant acceleration. We're actually going to derive it ourselves. So Newtonian. The Newtonian way is to recognize the forces. The net force is equal to the sum of all the particles' acceleration. So you can think of it like this. Now this looks pretty complicated, but in reality, for x and y, let's see here. For x and y, oops. Wait, I already messed it up. Okay, you should cut this part. Alright, we're gonna cut that. So it's been a while since I did this. So the acceleration is equal to the sum of all the forces. There you go, that's the Newtonian way. This looks complicated, but it's pretty easy. We just recognize that there's one force acting on this ball, which is the, I should write in a vector form. So the vector force is equal to 0, negative mg for the y. So there's no acceleration in the x, and there's negative mg acceleration in the y. This is simple. Very simple. So we get m, y double dot, is equal to negative mg. And then we solve this differential equation by first canceling out the masses. So we just get the acceleration is equal to some constant. We just integrate with respect to time. From what? T naught, which is 0, to our time t. So we start at 0 to some time. This is going to give us y dot is equal to negative gt plus some constant, which we'll call a. Then we integrate again to get, oops, that's a terrible y. Y is equal to negative 1/2 gt squared plus, so that constant times t, and I'm going to have to introduce another constant, the constant of integration. It's a little bit out of the screen. That's supposed to be a y, just so you know. It's a little diagonal. I don't know why I draw like that. That's just my handwriting. So y equals all this. There we go. We solved it for y. If you're wondering what a is, in this case, you can solve for the constants by plugging in random values like oops, like we want can you undo? Thank you. Like we want the y at time equals 0 to equal a specific y naught, and this is going to give us b. Sweet. And we want the speed of y at time equals 0 equal to some specific vy naught, and you're going to determine that this is actually just going to be a. So the constants are really easy to define, but this is the physical interpretation of the constants. Cool, cool. Alright, so that right there is the Newtonian way. We simply recognize the forces, write out the differential equations, and yeah, we perform all this math. Keep in mind that this Newtonian way, the form does change depending on the coordinate system, so we were using Cartesian here. So it's very simple. It's just going to be x double dot. I should write this. So, oops. So the second time derivative of position is simply x double dot, y double dot, z double dot. There you go. That's how you write in Cartesian coordinates. However, in polar coordinates, let's say we were to use polar coordinates, it's gonna equal something else, something a little more complicated. Let's see here. See if I remember. R double dot, the magnitude, the distance from the origin. Not like that any of this matters, but you know, it's just cool to show anyways. R hat, R phi double dot plus 2R dot phi dot. As you can see, I'm just showing, you don't have to know what the heck is going on here, but I'm just showing you that the form does change drastically. This MR double dot, depending on the coordinate system we're using here. In polar coordinates, as you can see, it is very different and much more complicated than Cartesian. So that's the disadvantage of Newtonian mechanics. I'm going to need to take a deep breath in. I don't know how to cancel out my breath. I'll work on that. OBS doesn't know how to cancel out my breath, so you're going to hear some of my breathing in the background while I try to catch my breath, because I don't usually talk this much. Taking a sip of water. Okay, Lagrangian way. Lagrangian way. This is the equations. You want to know where they come from. Basically, partial derivative of Lagrangian with respect to some generalized coordinate. General as in it could be any coordinate. And the time derivative of the partial derivative of Lagrangian with respect to the speed of the generalized coordinate. This right here is when people get really confused. But don't worry, partial derivative is just a regular derivative, except you treat everything, you treat all this stuff as constants. That's pretty much it. It's very easy. So you don't really think about like time dependencies or whether the subcoordinate is changing with respect to time. Partial derivatives are actually even simpler than regular derivatives in some cases. Not saying partial differential equations are, though. They are tough to solve. Okay. And the Lagrangian is defined as the total kinetic energy minus the total potential energy of the system. So to keep in mind, you will get a bunch of these depending how many generalized coordinates you have, or degrees of freedom, we like to call it. So the more degrees of freedom the system has, the more partial derivative Lagrangian equations you have to solve. But basically, this equation will give you the differential equations, the equations of motion. So you can solve them. It doesn't guarantee that the differential equations will be easy to solve, but you'll see that they're pretty much the exact same as if we did it any other way. But there are advantages to using the Lagrangian way. So let's see here. Let's start with Lagrangian. So we're doing free fall, remember. So first we need to define the potential energy. Like I said, I'm hoping that if you got to this point, you at least know some basic physics, like how to define potential energy for height. There you go, mgy. The height of our ball is y at all times, remember? Simple. Okay, kinetic energy you may know as 1/2 mass times v squared. Now this v squared doesn't really help us because we're actually going to want our generalized coordinates to be in x and y. This v isn't really a generalized coordinate, it's just saying that the kinetic energy is proportional to the square of the velocity. How do you represent the square of the velocity in terms of our Cartesian coordinates? Well, that's simple. Since v, some vector algebra for you, is v is equal to the magnitude of velocity, and since it's squared, v squared is equal to the magnitude of the vector velocity squared. So that means it's equal to x dot squared plus y dot squared. Right, the magnitude of the velocity is going to be the square root of this, but since we're squaring it, it's x dot squared plus y dot squared. It's pretty easy, pretty cool. So let's get rid of this. If you can't tell, I'm using Microsoft Paint. Nothing wrong with that. It's a free open source software. Don't make fun of me. Okay. See, that's kinetic energy in my terrible handwriting. You know what? Let's rewrite that. So the kinetic energy is going to be x dot squared plus y dot squared. There you go. So since this is actually the total kinetic energy of the system, there's only one object in our system, the ball, and one potential energy, because there's only one object. Okay, so this is actually everything for the full system. So combining it all, I'm just practically rewriting everything pretty much, but it's going to be easier to see because of this negative sign. We're actually going to be subtracting potential energy. Remember that. We are subtracting. Now we just perform the partial derivatives that the Lagrangian equation tells you to do. The first one, let's go with x. X dot. Perfect. So this is our first generalized coordinate. Notice how the Lagrangian, where the Euler-Lagrange equation stays in the exact same form regardless of the coordinate system I'm going to use, because it says generalized coordinate. So if we would have a problem that we have to write in polar coordinates, it would actually take the same form. It's really cool. One of the main advantages. Alright. Okay, so let's perform the left-hand side. Partial derivative of Lagrangian with respect to x. Well, if you look at the Lagrangian, there's no x. Remember, a partial derivative just treats whatever is here as as the variable. It's just a regular derivative as if it's taking the derivative of this variable but treating everything else as a constant. So this x dot, y doesn't matter, y dot doesn't matter. So it's all 0. There you go. I know, confusing. How is this going to give us the equations of motion? You will see it is magical. Okay, then the time derivative of this, which is the partial, some of my words, x dot, derivative with respect to x dot. As you can see, we have the x dot here. Remember, it's just treated like a constant. Don't worry, I know it's a little confusing. That 2, power rule, hops out front, cancels with the 1/2. X dot. Now we have a regular derivative, so now we do have to actually worry about time dependencies and stuff, but luckily mass doesn't change with time. So it's just going to be x double dot. If it did change with time, then we'll have like m dot x dot plus m, which gives some cool equations in and of itself if you do have systems with mass changing, like a rocket, I guess, for example. I actually never applied Lagrangian mechanics to a rocket. I'm not sure how it will work. I should look into that. Mx double dot. This is a differential equation that's uncoupled. Cancel out the m with the 0 there. It's uncoupled. We get our differential equation is just equal to 0. This is one of the easiest differential equations to solve. It's like what babies learn in kindergarten. And you can see that it'll just take this form, where a and b are just some random constants. A happens to represent Vx naught, and b happens to represent x naught. There you go. Cool. We did actually do that in the Newtonian way. We kind of just ignored x, but I mean x, there's no force in the x direction, so we would have gotten the same thing. X double dot is equal to 0. Oh, I need a little break. Alright. Y's turn. Partial derivative with respect to y. Just writing it out so you can see a little more clearly. My voice. Y. Well, in this case, we do actually have a y. It is right there. So it's just going to be a negative mg. This term is 0 because it doesn't depend on y. Time derivative Lagrangian with respect to y dot is going to equal m y dot, and then we have the derivative, which is going to be my double dot, which is the exact same differential equation we solved the Newtonian way, and you already know the form of that. There we go. So you may ask yourself, what the heck is the purpose of Lagrangian mechanics if it just gives us the exact same thing as if we did Newtonian mechanics? Well, like I said, there are many, many distinct advantages to the Lagrangian way versus Newtonian way. The first advantage that I already showed you is that it's the same for any coordinate system you use. It takes the exact same form. Unlike Newtonian, which has to change form, and sometimes it gets a lot more complicated, like I showed you with polar coordinates. So that's the first advantage. Second advantage, that's the second advantage. Second advantage is, I don't remember. It has something to do with forces? No. Oh wait, constraints. Yes, constraints. It works, it eliminates constraint forces and you don't have to worry about them. Newtonian does have to worry about constraints and stuff, and constraints make things way more complicated. Lagrangian mechanics just completely eliminates them out of the picture. Not super useful if you need them for like working with tension or friction, or like if you're an engineer and you want to determine if a bridge will collapse. Lagrangian mechanics just says it doesn't care if the bridge will collapse or not. This is what would happen if it didn't. So yes, that's Lagrangian mechanics. It works in very ideal systems where there's no dissipative forces. I mean, not the best all the time for classical mechanics, but for like quantum mechanics and particles where there's no dissipative forces, it's really useful. Well, actually, we don't really use Lagrangian mechanics for quantum mechanics. I'm pretty sure. I think there's a formulation. It's Hamiltonian. Hamiltonian mechanics is next. This is what they use, those big quantum physics boys that know what's up. I don't know quantum physics, but I do know Hamiltonian mechanics. It's pretty similar to Lagrangian, honestly, and it has some cool advantages. Like let's see here. Well, first off, the Hamiltonian is just a quantity, just like the Lagrangian is. Oh, shoot, my hand. What's up with my handwriting? It was just good a second ago. That is terrible. I'm trying to make a summation sign, if you can't tell. Summation. There you go. Oh my goodness. What is it? P I Q I dot minus the Lagrangian. Yes, so see, you can see the Hamiltonian contains the Lagrangian, and Pi is now a new quantity that is going to be the generalized momentum. Generalized momentum is defined as the partial Lagrangian with respect to Q dot I. Okay? And what's cool about the Hamiltonian is that if the system is time independent, which usually it is, it's just written as the total energy of the system. This is very useful because instead of working with whatever this is, we just work with kinetic plus potential, which is much easier. Alrighty, let's get started. Oh yeah, wait, the actual equations of motion. P dot is equal, wait, I like to start off with Q dot for a very particular reason. So it is just going to be this, pretty easy. And we got our second, there's actually two equations of motion. The Hamiltonian equations, there you go. So this is what gives you the equation of motion. Notice how it will give you 2 instead of 1 like the Lagrangian does for every degree of freedom. And they're all first degree, so it will give you 2 first degree differential equations. The Lagrangian will give you 1 second degree differential equation, which has its advantages. It has its advantages. Alright. Man, I've been talking for so long, this is giving me a throat ache. I'll get used to it. Alright. Let's undo whatever I just did. Alright, let's write the Hamiltonian. This is the first step. So, total kinetic energy, we've already figured this out. And the potential energy. And this time we're adding it. So this just looks like the total energy of the system. However, we gotta do one thing, and that's to ignore whatever this is and define our generalized momentum. And we already know our momentum for the Cartesian coordinates. There you go. And then we just solve for x dot and y dot, and what we do is we just plug these in to get the actual form that we need. There we go. Now, what we're going to do is use the Hamiltonian equations for both x and y. So for here, we get x dot is equal to derivative with respect to px. Wow, doesn't that look familiar? Doesn't that look familiar? Once again, if you don't even know what Lagrangian mechanics is, you may ask yourself, what the heck is the point of this? Well, once again, your puny mind can't understand the significance of Hamiltonian, because I don't even understand the advantages of using this in, like, the classical world. I know it has advantages in quantum, but I can't see it in classical. I've barely studied it though, so like I said, I've applied it to many systems, but I still, like, I've literally did every problem in the textbook, and I still don't understand, like, what's the purpose of it? Why do we need a Hamiltonian? It was an optional chapter though, I'll give it that. Alright, someone explain to me in the comments below. And P1, wait, what is it? That's what happens when I do math while talking. What is this? Do you see partial derivative with respect to y? No. This section is just going to be 0. This is going to be equal to a negative mg. There you have it. I'm too tired to explain. Basically, you have 2 or 4 first order differential equations that are coupled. And instead of solving them by, like, substituting px here and getting x double dot is equal to 0, whatnot, you solve them an even better way, which is to just, like, kind of guess. Well, let's see here. I don't even know if that's possible. Px of t We know px of t is just equal to some constant, and x of t is equal to px over m. I don't know, actually, what is going on. Should I just omit Hamiltonian? What was the purpose of this? I don't even understand Hamiltonian that well. You can just, like, skip all that solving first order differential equations and just combine them all into one equation, which I find easier. So it's just taking derivatives of both sides. You get px dot over m, and we know px dot is always 0, so this is 0. Here, y double dot is equal to py dot over m. We know what py dot is just equal to negative mg. So y double dot is equal to negative g. There you go. We can transform first order differential equations into second, and I guess vice versa. That's the advantage of Hamiltonian first order differential equations, and you can also like plot them on a phase space diagram, which I'm honestly too tired to explain. I'll think about making a video about that later because it is pretty interesting. All right, bye bye.